For those motor load system which have lower inertia, your transient may die out in a shorter period of time. Whereas those which are having higher inertia, in those cases, this transient may or starting period may be sustained for a longer period, right? It may take a longer period. So in those machines where this motor load system have high inertia, we had to use these starters because this high starting current for a longer period, right? It may overheat your machine, and it because of this overheating, your insulation may damage, because of which your windings may also be damaged. I guess it is clear to the class. Why do we use starters, right? After discussing the starters for the induction motor, we start discussing about the speed control methods for the induction motors, right? And as a speed control methods, we discussed that these are the important, some of the fundamental, in fact, fundamental methods of the speed control for induction motors, right? And in this, the first method is the pole changing, whereas the other is the supply frequency control. Third one is the stator voltage control, fourth one is the rotor resistance control, and fifth one is the slip power recovery. In our last class, we studied about the pole changing method, right? And how does this pole changing method, how we can use this pole changing method to control the speed of the motor? What is the basic behind this? Basic is, raise your hand who knows the basics of this. Again,
P.
P. Okay. So Akshay, can you add on something to this, or can you explain it in a better way? What Sunil is saying is that we know that the synchronous speed is dependent upon the pole of the motor as well as the frequency of the supply, right? So if we increase or decrease this number of poles, your speed will correspondingly increase or decrease. If suppose we are increasing the poles, your speed will decrease, and if we are decreasing the poles, your speed will increase, right? So by changing the number of poles, we can change the speed. Obviously, these poles will be increased or decreased in discrete steps because your poles occurs in pole pairs, right? We may have two pole, we may have six pole, we may have four pole, right? So the pole will be in even numbers, right? We have even poles only. We cannot have an odd number of poles. So correspondingly, the speed will also be in these steps or corresponding to these poles. Is this fine, bacho? Say yes or no.
Yes, sir.
Right. So we discussed this, and even we have discussed a case. Ki suppose in the stator winding we have the 6 coils, right? What we did is we have divided these coils into 2 coil groups, each containing the 3 coils, right? But we discussed, in fact, that how can we have 6 and 12 poles from these 6 windings by have a change in the interconnection only, right? So this was the example that we can generate the 12 number of poles if we feed our supply, if we feed these windings in this way, right? If we connect them in this way, they will be generating the 12 poles, right? And if we connect this, if we connect this A like this way, means instead of here being connecting this A to this side, if we connect or if we feed it through this supply like this way, if we feed it over here and we connect this to this, in that case how many poles will be generated? अगर कनेक्शन इस तरह से करेंगे तो कितने पोल्स बनेंगे? टेल मी, अगर ये कनेक्शन इस तरह से है तो पोल कितने जनरेट होंगे? 6 poles, because the current in the first coil group, it is from left to right, that's why it will be generating the pole in one of the direction, whereas in the second coil group the current is being flowing from right to left. So it is because of the direction only they will be generating the different poles. If your upper one will be generating the north pole, then down coil will be generating the south pole, right? So because of that, there will be only total 6 poles. But if we interchange the connections, we may have the 12 poles from these 6 coils only, right? And we discussed it in the yesterday's class. Then we started discussing about the stator voltage control, right? And we have studied that your stator voltage can be used to control the speed of the induction motor, right? We also know this fact that your torque of the induction motor, it is directly proportional to the square of the voltage. That means if we are reducing the voltage, that means your torque will also going to reduce, right? So what happens is this speed control method is suitable only for those applications where in the decrement in the speed, your load torque demand also decreases, right? And such kind of profile is being found for fan and pump drives. That's why this stator voltage control is mainly being applied to the fan and pump drives where your torque demand also reduces with the speed, right? We we were discussing about the one of the concept, how can we have this stator voltage control. So if these are the supply voltage to us, what we can do is we can attach a one voltage controller, AC voltage controller, in between the motor and the supply. So by controlling these firing angles of the AC voltage controller, we can control the supply voltage to this motor. I guess it is very clear to the class, right? Is this clear? You already could have studied about these AC thyristor voltage controllers or AC voltage controllers, right? Let us do our numerical on this, and things I guess will be more clear to you if we'll be able to solve this numerical, and if we'll be able to understand this numerical, right? Numerical is an example which is being given in the book 6.8. It's a solved example, right? And what they are saying is a 2.8 kilowatt, 400 volt, 50 hertz, 4 pole, right? 1370 rpm, 1370 rpm, delta connected squirrel cage induction motor, has following parameters, refer to stator, right? Refer to stator. And what are the parameters? The parameters are the stator resistance Rs, and it is equals to 2 ohm, right? The RR dash, that is being rotor resistance, referred to stator side, and its value is 5 ohm, right? The stator side reactance and the rotor side reactance referred to stator is equals to 5 ohm. The magnetizing reactance XM, right, is equals to 80 ohm. So these are the parameters which are being given. Okay. What we had to do is, what they are saying is, they are saying that motor speed is controlled by stator voltage control, right? By stator voltage control, as the method which we just have discussed, right? Now they are saying that when this motor speed load, when this driving system is driving a load, when driving a fan load, it runs at rated speed. It runs at rated speed at rated voltage. Means when we apply a rated voltage, it will run at rated speed with this load, fan load, right? So they have given us that this motor is being coupled to the fan load, and when we apply the rated voltage, it will run at rated speed, right? What we had to calculate is, we have to calculate They want us to calculate the motor terminal voltage. I will calculate motor terminal voltage, current and torque at 1200 rpm, and right, suppose this is the case, right? This is the case. We have an induction motor which is of a 2.8 kilowatt, 400 volts rated voltage, and 50 hertz of supply, means it requires 50 hertz of supply. 4 पोल मोटर है, 370 आरपीएम पे चलती है, राइट, और डेल्टा कनेक्टेड है, जिसके जो इंटरनल पैरामीटर्स हैं वो ये हैं. वो कह रहे हैं कि इट इज बीइंग, द स्पीड ऑफ दिस मोटर इज बीइंग कंट्रोल्ड बाय स्टेटर वोल्टेज and it is being driving a fan load, right? And that fan load is such that it runs with the rated speed when we apply the rated voltage, right? So let us solve this numerical. I guess every student of this class now can tell me about the synchronous speed for this motor. How much will be the synchronous speed? Write your answer in the chat box. What is about the synchronous speed? Can you calculate a synchronous speed for this motor? Give me the value of synchronous speed. I got the answer from, write it in the chat box. What will be the synchronous speed? Sunil, Rudendru, Deepak. What about others? Write your answer. Only 4 students have written this answer. Everybody who is being present in the class, write your answer. Write your answer. Still not being, I haven't got the answer from all the students who are being attending this class. Only 1, 2, 3, 4, 5, only 10 people have written their answer. Everybody, write your answer in the chat box. Write your answer in the chat box. How much will be the synchronous speed? The synchronous speed is being defined as Ns equals to 120 F by P. And for this case, we know that how much is the frequency? The frequency is 50 hertz, whereas this motor is of 4 pole. So if this is a 4 pole, that means your synchronous speed will be 1500 rpm, right? If you know the Ns, can you find the value of slip at full load? What will be the slip at full load? At full load, slip will be, slip we know that it is equals to Ns minus Nr over Ns. How much will be the value of slip? Write your answer in the chat box. The value of slip at full load. We are talking slip at full load, right? The slip at full load will be, Ns value is 1500, whereas at full load, at rated speed, it runs with the rated speed, right? They are saying that when it runs at this load, at rated voltage, it runs with this rated speed. So it is 1500 minus 1370 divided by 1500. How much is the answer? Write your answer. Write your answer. Sunil is saying that it will be 0.09. Write your answer. I will be marking your attendance with this only. Write your answer. What will be the value of slip at full load? And let us see, and I will give you the one more mark in class assessment if you answer the one. जो सबसे पहले आंसर करेगा उसको 1 नंबर ज्यादा मिलेगा. Tell me the value of slip when it will be running at 1200 rpm. क्वेश्चन में पूछा गया है कि 1200 आरपीएम पे हमें बताना है सब चीज. तो क्या मुझे बता सकते हैं कि 1200 आरपीएम पे स्लिप कितनी होगी? राइट द आंसर इन द चैट बॉक्स. What will be the value of slip at 1200 rpm for this motor? How much will be the slip? How much?
Sir, 0.2.
0.2. बताओ भाई, सब बताओ जल्दी
Yes,
जल्दी।
sir.
Yes, sir.
Right, it will be 0.2. So at 1200 rpm, the value of slip will be slip 1200, we can write as, it will be ns, that is 1500 minus 1200 divided by 1500, so it will be 0.2. So we can see that your slip is going to change with the change in speed. Earlier, when your motor will be running at this speed, your slip will be this. But at 1200, slip will be increased to 0.2. Right. Let us see towards this numerical what they want us to calculate. They want us to calculate the motor terminal voltage, the voltage which we needs to apply, right, when your motor will be running at 1200 rpm. We know this fact that when we will be applying 400 volts, right, your motor will be running at 370 rpm. So obviously we need to decrease this voltage to get the reduced speed, which will be lesser than the 370. But how much that voltage will be, how can we compute this? For computing this, let us take how can we do this? See, for that what we can do is we can calculate the torque, right? We can calculate the torque that will be generated at full load. So at full load, how much will be the torque? We know the expression. At full load, the value of the torque generated will be, how much it will be? We know the expression. It is 3 by omega s into V square over Rs plus Rr dash by s. Give me the value of this square plus xs plus xr dash chi square into Rr dash by s, right? Into Rr dash by s. How much is the value? बताओ, how much will be the torque value? Torque at full load. This will be the torque at full load. Give me the answers. We know this value of slip. How much will be the value of slip for this case? It will be 0.0867, right? Because we are talking about the full load torque, that is TFL. So at full load, your slip will be slip at full load. It will be SFL, right? This one. So at full load, this will be S of FL. Use the value of SFL. We know the value of voltage, that is 400 volts, right? We know the value of resistance. We know the value of reactance for stator as well as rotor. So how much will be the full load torque value? होता है उसी समय पे वो बोल रहे हैं कि when driving a fan load it runs at rated speed at rated voltage, right? तो इसका मतलब जब वो रेटेड स्पीड पे जितने टॉर्क के साथ चल रही है वो फैन लोड का टॉर्क होगा। ये हमने पढ़ा भी है कि एट स्टेडी स्टेट योर टीएल मस्ट बी इक्वल टू टी। सो एट फुल लोड जो भी पंप लोड होगा दैट पंप लोड मस्ट बी इक्वल टू द मोटर टॉर्क। टीएल फॉर दिस केस इज द पंप लोड, right? Pump load as being discussed even in the last class, TL, that means pump load, right, is can be, they have an equation, this load can be expressed as K of 1 minus S of a square, right, where S is the slip. So we can write this as that this TL is equals to Tm, that is equals to 48.13. So from here, because we know that it will be slip at full load, so can we have a value of K from here? How much will be the value of K? K will be equals to 48.13 divided by 1 minus 0.0867 chi square, and that will be equals to, how much will be the value of K then? It will be equals to, write your answer. अरे दो दो तीन तीन बच्चे आंसर कर रहे हैं, जल्दी बताइए। You don't have calculator? At least you should have the, I guess you will be using the mobile phone or the computer. How much will be the value of k? It will be equals to 57.7. It is 57.7 if we use the value of slip as 0.0867, right? So it will be k. So that means if value of k is this, so this your load characteristic can be represented as 57 point say in 0.7 into 1 minus s of square, right? This will be the final expression. Now what will happen if when your speed when motor speed is 1200 rpm, right? At that case slip at 1200 rpm will be 0.2. We have calculated, right? 1200 rpm पे स्लिप हमने निकाली, इसकी वैल्यू 2 थी. तो how much will be the load torque that will be required at 1200 rpm? How much will be the value? जरा बताइए जरा. Write your answer in the chat box. देखते हैं सबसे पहले कौन लिखता है. Give me the answer of load torque that will be required to be generated by the motor when your motor will be running at 1200 rpm. 36.9. The value of load torque at 1200 rpm will be 36.9. Now we know that your motor at 1200 rpm has to generate 36.9 of torque. So this load torque or this torque required must be supplied by the motor torque, and we know that motor torque is equals to 3 by omega s divided by v square rs plus rr dash by s. Now this s will be changed because we need to get this at 1200 rpm, right? So square plus xs plus xr dash chi square into rr dash by s at 1200. So this must be have this value. We know this. We know the values of this and this, or even this one. So can we have the value of V from here? So that will be the voltage that needs to be applied to this motor when your motor will be running at 1200 rpm. So how much will be the voltage that we need to apply? Write your answers, that how much will be the voltage, value of voltage that we need to apply, and that will be the answer to the question. $253. And who was the first to answer? Astu was the one. Very good, Astu. Yes, 253 volts will be the answer. That we need to apply that much of voltage to run our motor at 1200 rpm such that it generates the torque of 36.9 Newton meter. Right? I guess it is very clear to the class.
सर ये 253 है सर, 225 नहीं लिया सर, आपने 235 लिख दिया उसमें.
अच्छा ठीक है, कोई नहीं, मैं चेंज कर देता हूँ, है ना. इट विल बी 253, राइट. इट विल बी 253 वोल्ट. अच्छा, एक और कंसेप्ट था बीच में. दे हैव told us that this motor is a delta connected. What was the use of this? Why he has given this information? Because this 400 volts is basically the line voltage, and in case of delta we know that your line voltage will be equals to phase voltage. That's why we directly have used this V, right? I guess it is clear to the class, and you know this, all these facts, these are the basics, right? They want us to calculate the voltage, we have calculated. What else they want us to calculate is the current that your motor will be taking when we will be applying this voltage, right? Obviously the current, that is the rotor current, will be equals to the applied voltage divided by the impedance of the circuit. And impedance, we know that it is equals to Rs plus Rr dash by S plus J times of XS plus XR dash, or under root of this square plus this square, right? So how much will be the value of current that motor will be taking at 1200 rpm? Hmm? बताइए. That would be the rotor current IR dash. How much will be that IR dash? बताइए जरा, कितनी होगी बच्चों? कॉपी चल गया, कैसे आंसर आया, कौन बताएगा? सही है, बहुत बढ़िया. ये आंसर नहीं आएगा
सर 8.973.
हाँ, it will be 8.973. It will not be 17.89 या 10.3 समथिंग. कितना लिखा? 17 लिख दिया सीधे सीधे सीधे. सुनील कैसे बनाया भैया ये? सुनील
यस सर.
बताओ जरा कैसा आया? IR डैश की वैल्यू ये होगी, है ना? दैट विल बी RS प्लस XS प्लस और RS प्लस RR डैश बाय S plus J times XS plus XR dash. This will be the value of IR, but that will not be the total value. Total value will be the IS that will be taken from the supply, and that will be equals to IR dash plus vector sum of IM. So your IS will be a vector sum of IM plus IR dash. Is this clear?
Yes sir.
So they in the book what they did is they had added these two values. They have calculated the IR dash value, then they have calculated the value of IM. That will be equals to the applied voltage divided by this reactance XM. Right? So J times of this will be the value of value for this IM. Is this clear? And after adding this IR dash and IM, we will get IS. That will be equals to 10 point something. That is coming as 10.38, 10.328 angle of minus 37 degree with angle of minus 37 degree, right? And as your motor is delta connected, we can have this as line current, and your line current will be equal to √3 times of phase current in case of delta connection. That's why the answer, final answer will be 17.89 ampere. I guess now it's been clear to the class how they have calculated, how will do this. Is this clear बच्चों? बताओ भाई.
Yes sir, it's clear.
Right. Let us move ahead and let us discuss about one of the method that is being mentioned as variable frequency control. Right? Variable frequency control, but with the variable voltage source, from a voltage source. Right? Now, we already know that synchronous speed, we know that it is being directly proportional to the speed, to the frequency, right? So synchronous speed, and therefore the motor speed, right? The motor speed can be varied, right? Can be controlled by controlling the frequency of the supply, by varying frequency supply, a supply frequency. I guess you all will agree to this statement, right? Say yes or no.
Yes, sir.
Right. How many of you agree to this statement? Raise your hands, please. That we can vary the synchronous speed by varying the supply frequency. How many of you agree to this? Only few people? Again, that means you are not listening to me. Oh, okay. Right. So we can vary because we have learned that your synchronous speed is nothing but it is the 120 f by p. That means by varying this frequency, we can vary the synchronous speed. And as we can vary the synchronous speed, we can vary the motor speed. That means, consequently, we can say that by varying the frequency, we can vary the motor speed. There is no doubt over this, right? But we also have learned, what we have learned is, कि when we apply the voltage across the stator of the motor, when we apply the three-phase supply across the stator of the motor, right, an EMF is induced on the stator side as well as on the rotor side, right? The stator side induced EMF E1, right? It can be given by an expression 4.44 F phi m N1, right, where N1 represent the stator side turns, stator winding turns into kW. And it is, this expression is similar to the EMF equation of a transformer, except this kW, where this kW means the winding factor. So this winding factor is being constant. 4.44 is also constant, right? This n is the number of turns on the stator winding, right, in the stator winding. So we can say that your E1 is proportional to F phi m, right? If we neglect the stator drop, voltage drop, then E1 will be equals to V1 or V applied voltage. Yes or no? So V, if we neglect this, your V will be equals to E1, and that is being proportional to pi F phi. So from here, can we write this as V by F is proportional to phi? Yes or no?
Yes, sir. Yes, sir.
Right? So see, what we have learned is that by changing the frequency, we can vary the speed of the induction motor. Right? But on this frequency, your flux also depends. In fact, it depends upon the ratio of this V by F. Now, what is the relation of these two? Why I am telling that this relationship along with this one? There are two relationships, right? One is saying that by varying the frequency, we can vary the speed. And again, this is saying that if we vary the flux, if we vary the frequency, your flux is going to vary, right? Now see, why we are discussing this? We are discussing this because any reduction, what will happen? Any reduction in supply frequency, any reduction in the supply frequency, right, without changing the terminal voltage, what will happen because of this? What will happen to the flux? If we reduce this frequency without changing this voltage, what will happen to flux? Your flux will
increase.
Right. Your flux will increase, right? That causes an increase in flux, increase in the air gap flux, right? In the air gap flux. Now, we know this fact that induction motors are designed in such a way that they always operates at the knee point of the BH curve to make the best utilization of the material by which they have been made, right? So what will happen if we reduce the supply frequency without changing the voltage? That will make this motor to run into the saturation region, right? Is this point clear?
Yes, sir.
Right? If we reduce the frequency without changing the voltage, that will make this motor to run into the saturation region. Therefore, right, this will make motor to go into saturation region, right? Now, because of this saturation or because of this, what will happen? Your motor, this will make, or this will increase, or your motor will take, this will increase. In turn, what will happen? This will increase the magnetizing current, right? What else? Because of this will happen? It will increase the magnetizing current. It will distort the line current. It will distort the line current, right? As well as voltage, line current and voltage. Along with this, it will increase the core loss. This will increase the core loss, and in fact the stator copper loss. Right? Along with it will also produce a high acoustic noise, produce a high pitch acoustic noise, right? So this will happen, right? If we reduce the supply frequency without reducing or without changing terminal voltage, right? So what will happen? These losses will occur, and this will happen to the motor. That's why what is being done? Your voltage is also being reduced along with the frequency, such that your flux may be kept constant, right? So what we do? We reduce the voltage along with the frequency to keep this flux constant, right? So when we reduce this, we also reduces the voltage, right? When we reduce this, we also reduce the voltage, and the operation is called as variable voltage, variable frequency operation. Is this clear? What we call it as variable voltage, variable frequency, and the drive is called as variable voltage, variable frequency drive, VVVF drive, right? And this will be doing by reducing the supply voltage along with the decrement in the frequency, such that your flux can remain constant, right? Now, while increase in the flux beyond the rated is undesirable from the consideration of saturation effect, your decrement in the flux is also avoided to retain the torque capability. See, we have learned that your torque is also proportional to this flux, right? Torque is phi into Ia in case of DC motors, but in case of induction motor, the torque is also being proportional to flux. So once we have seen that by decreasing the frequency, we don't want to get your flux saturated. Also, with the increment in the frequency, we don't want your flux to be weakened, because if your flux will be weakened, then your torque capability of the motor is going to reduce, right? So on both the sides, we don't want this flux to be changed much. On the one side, we don't want to get your motor into the saturation region, whereas on the other side, we don't even want to weaken this flux, such that we want to retain the capability, right? We will reduce this flux, but we don't allow it after a certain point. I guess it is very clear to the, right? That's why what happens is we keep this flux at rated value by changing the voltage along with the frequency, and the operation is called as variable voltage, variable frequency operation. Is this clear, बच्चों?
Yes, sir.
Right. चलो आज के लिए इतना ही काफी है, फिर पढ़ेंगे।